This is the second video for the AP packet on kinematics. Number 68 says a snail moving along a straight line. Its initial position is x sub 0 is equal to -5 meters, and it's moving away from the origin and slowing down. In this coordinate system, the signs of the initial position, initial velocity, and acceleration, respectively, are... All right, so here's the snail. It is moving in the opposite direction. So it's moving in the negative direction. Because it's moving in the negative direction, its velocity is also negative. However, if it is slowing down, remember we have opposite signs. That is, if the velocity is positive, then the acceleration is negative. That would be slowing down. If the velocity is negative, then the acceleration must be positive for it to slow down. And so B is the correct answer here. Okay, number 69, a rock is dropped from the top of a tall tower. Half a second later, another rock, twice as massive as the first, is dropped. Ignoring air resistance, what happens? Okay, first of all, this bit about twice as massive, we talked about that on the other side. Mass does not come into play here, so we don't care about mass. Next, let's look at this rock, and I'm going to draw one of those dot diagrams. So remember, as it's accelerating, these dots are getting farther and farther apart, right? It's going farther and farther because it's accelerating. Okay, so as this is falling, let's say it's at this position here, and right when it gets there, you are going to take another rock and you are going to drop it, and it is going to have a similar, or exactly the same actually, dot diagram, but it's a half a second later. So this one's up here and this one's down here. Okay, notice these positions are getting farther and farther apart, as are these. But because these are starting out smaller, the red ones are getting even greater. So in other words, this is going to get farther and farther and farther. This one's never going to catch up. In fact, let's look at the options. The distance between the rocks increases while both are falling. Okay, so this is what I'm talking about. If this is getting farther and farther and farther, so is this one, but its margin is not as great ever. It's never going to catch up, right? So I would say that A is true. Okay, part B, the acceleration is greater for the more massive rock. That's not true. Acceleration is always -9.8, so that's not true. They strike the ground more than half a second apart. Let's think about that. Lastly, they strike the ground with the same kinetic energy. Okay, kinetic energy, we haven't even talked about kinetic energy. That's not going to be our answer because we haven't even talked about it. So we're down to A and C. The distance between the rock increases while both are falling. That's true. Part C, let's think about that. They strike the ground more than half a second apart. No, it's actually exactly half a second apart. Because if you drop this rock, it's going to have a certain time that it's going to take to reach the bottom. Well, that other rock, it's going to have that exact same time. And so if you drop it half a second later, it's going to be a half a second later that it falls. So A is the only correct answer on number 69. All right, number 70. A car is initially moving at 0.5 meters per second along a track. That's our initial velocity. It comes to rest after traveling 1 meter. The experiment is repeated on the same track, but now the car is initially moving at 1 meter per second. How far does it travel before coming to rest? It doesn't say so, but something is making it slow down. Something is impeding it. Something is in its way. Because if there wasn't, it wouldn't slow down. It would continue on with the same velocity. So something is making it slow down. I don't know what that is. It might be friction. It might be a ramp of some sort, but something is making it slow down. And so basically what's implied here is there is acceleration. It is slowing down, so there is acceleration. That's one thing we have to consider. Let's utilize the equation final velocity squared is equal to initial velocity squared plus 2a delta x. Let's use this equation and see what we can make of it. So I'm going to use this equation for the first cart, and the first cart, its final velocity is 0. Its initial velocity is 0.5, and I'm supposed to square that. And I don't know what the acceleration is, but the distance is 1 meter. So now I can solve this for A. So I'm going to subtract this to the other side, which is going to give me a negative 0.25. And then over on the right-hand side, I'm going to get 2A. I need to divide by 2, and so my acceleration is negative 0.125 meters per second squared. Okay, so now if we do that same thing with the other cart, we're going to use that same equation again. So once again, my final velocity is 0. My initial velocity this time is 1, and I need to square that, and plus 2a delta x. For my acceleration, I'm going to use the same acceleration as the other cart because remember at the beginning I said something is slowing it down. I don't know what is slowing it down. It might be friction, it might be a ramp. Okay, well, whatever that is, that acceleration is the same acceleration that this cart is going to be experiencing. Like, let's just say it's friction. Okay, if it's friction, then it's the same amount of friction that's impeding this cart as well. And so I'm going to use that same number as the acceleration for this cart as I did for the first cart. So if I continue on and I continue working on this, I have 0 is equal to 1. I have minus 0.25 delta x. I'm going to subtract my 1. I'm going to divide by 0.25, or negative 0.25. And so for this cart, it's going 4 meters. The first one went 1 meter. This one is going to go 4 meters. The point that this question is trying to get at, which is a common point in physics, AP physics, is that just because something is doubling doesn't mean necessarily that the result is doubled. In other words, we had velocity of 0.5, and now we have velocity on the second one of 1. Just because I doubled that doesn't mean necessarily that the distance is going to be doubling. In this case, the distance actually gets quadrupled because I take the double and I square it. And that's what's causing, because we're taking the velocity squared, since we're squaring that velocity, that is what is giving us the 2 squared, which is 4, rather than just 2. And so that will come up quite a bit in AP Physics, and we have to look at the equations and figure out which equations are we supposed to be looking at, and when I double this, what does it do to that? And so that's what's going on here. All right, number 74. This is a velocity time graph. We have a car on a straight track. It's shown in the diagram. The thick line represents velocity. Assume the car starts at the origin at x equals 0. So it's starting at the origin at x equals 0. It's going at 7.5 meters per second. Doesn't that look like 7.5? I think so. And it has a constant velocity, and then it slows down. It hits a velocity of 0, and it starts going the other way, and then it continues on in the opposite direction. What's happening is, like, if this is the car is moving this way in the positive direction. It slows down. Maybe I'm going to do a dot diagram. Okay, at the beginning, my dots are all equal because it's the same velocity. And then it slows down, and it slows down so much that then it actually starts to go the other way. And then on this part, it is going the other way at that looks like a negative. Okay, hang on, I was wrong. I wasn't counting. Honestly, my glasses were not working well. So we're going to go back to this because this wasn't 7.5, was it? We're counting by 2, 4, 6, 8, 10. That 5 threw me off. So this is starting off at 2, 4, 6, 8 at a speed, a velocity of 8 meters per second here. And so down here, it is at negative 4 meters per second over here, okay? Going At 8 meters per second, it slows down, it turns the other way, and then it goes at 4 meters per second the other way, okay? Which technically means that these dots should be half the distance as they were up here. Okay, my dot diagram is kind of falling apart here, but that's the idea. That's what's going on. At which time is the car the greatest distance from the origin? Well, let's think about what we were just talking about. It's going, 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 going. Here's the origin. It's going, 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 going. It's slowing down, slowing down, slowing down. Stops instantaneously and turns around the other way. Where is it farthest from the origin? It's farthest from the origin out here. That happened right here at 5 seconds. Another way to think about it is we are talking about distance basically, and so we want to talk about distance on a velocity time graph. We can find the areas. And so if we look at this area and we calculate the area here is 24. The area here is 8. And let's come down here now. And this little triangle is a triangle of 2, and this is 16. And so it goes a total of 32 meters over here. I'm getting that because 24 plus 8. It then turns around and goes back 18 meters because a 2 and a 16. Okay, but the main thing that we need to know here is the greatest distance away from the origin was here at that 0. That's where it was farthest away because that's where it was turning around and coming back. Number 75, the average speed of the car for the 10-second interval. Remember, average speed is total distance over total time. It's not always a very helpful number, actually, but this is how we do it. And so the total distance traveled, okay, let's get back to these numbers we calculated just a second ago. We said it was a 32 this way and an 18 that way. Well, its total distance then is 32 plus 18, and the total time elapsed is 10. So the average speed is 5 meters per second. Notice it did say average speed and not average velocity. So the average velocity would have been different because it would have been displacement, but since they said speed, we used distance rather than displacement. That's why I added these two rather than subtracting them for the negative direction. Number 76, consider the motion of an object given by the position time graph shown. For what time is the speed of the object the greatest? Okay, if we have a position time graph, then speed is slope. So we're going to look for where does it have the greatest slope. They have some options here from 0 to 2. No, at that time the speed is 0. At 3 is right here, so we could calculate that slope. It's going down 2, 4, 6. Maybe just say 2, 4 to get some. So it's going down 2, 4 over 1. That's a negative 4. At time 4 would be right here. Oh, that looks steeper, doesn't it? I'm going to say that it's really hard to read, but it certainly looks steeper than the last one. And the last one says 8.5. That's going to be right here. That is not very steep. This is the steepest part. And so since it's the steepest, it is the fastest there. This next question is not related to the first question. A toy car moves 3 meters to the north in 1 second. The car then moves at 9 meters per second due south for 2 seconds. What is the average speed of the car for this 3-second trip? Okay, so once again, we're going to average speed is equal to total distance over total time. Okay, in the first second, it moves 3 meters in 1 second. Then it moves at 9 meters per second for 2 seconds. If it's going at 9 meters per second for 2 seconds, that seems like 18 meters to me. And that time was 2 seconds. What is the average speed of the car? So we have 21 divided by 3. That should be 7 meters per second. So number 78 is D. Okay, 79. I'm not sure if that 79 is on this page or the next. I'm going to go ahead and do number 79 on the next video.